67 kilometers. That is how far yesterday's earthquake near Antarctica sits from the epicenter of the largest quake ever recorded in that region, the magnitude 7.8 that tore open 300 kilometers of seafloor in 2013. That one did not arrive without warning. It opened with a moderate earthquake on the same side of the same fault, and 4 days later, the boundary broke. Nobody's predicting anything here. But scientists are watching this weekend, and by the end of this video, you will know the one number that tells you which way it goes. Yesterday morning, at 8:22 Universal Time, the United States Geological Survey recorded a magnitude 6.2 earthquake in the Scotia Sea. That is the stretch of the far South Atlantic that sits between the southern tip of South America and the Antarctic Peninsula, and it is one of the emptiest pieces of ocean anywhere on the planet. The agency put the depth at 10 kilometers, about 6.2 miles. The European Mediterranean Seismological Center came back independently with the same magnitude and the same depth. Nobody felt it. The nearest towns are more than 1,000 kilometers away. The survey listed the epicenter as 1,330 kilometers east-southeast of Tolhuin, Argentina, 1,368 kilometers east-southeast of Ushuaia, a city of 56,825 people, and 1,406 kilometers east-southeast of Rio Grande, in Tierra del Fuego. There is no city inside any radius where the shaking would have registered as anything at all. The survey issued a green alert through its rapid assessment system for both shaking-related deaths and economic losses. Green is the lowest level it has. 7 minutes after the event, at 8:29 Universal Time, the Pacific Tsunami Warning Center issued a statement confirming there was no tsunami threat. By every measure that a wire service uses to decide whether a story exists, this earthquake was a non-event, and on the routine reporting, that is exactly how it was handled. A moderate earthquake in open water. Nobody hurt. Nothing to see. That reporting is missing the only detail that matters. The epicenter of yesterday's earthquake sits at approximately 60.379 degrees south, 47.605 degrees west. On the 17th of November, 2013, the largest earthquake ever recorded anywhere in the Scotia Sea region struck at 60.27 degrees south, 46.40 degrees west. Run the Great Circle calculation between those 2 points, and you get approximately 67 kilometers, 42 miles. That is the distance from downtown Los Angeles to the far side of the San Bernardino Valley. On a plate boundary that is thousands of kilometers long, 67 kilometers is the same neighborhood. The 2013 event was a magnitude 7.7 in the survey's catalog and a magnitude 7.8 in the Global Centroid Moment Tensor catalog and in most of the published literature. Depending on which figure you use, it released somewhere between 250 and 350 times the energy of yesterday's earthquake. So yesterday's magnitude, 6.2, against the thing this fault has already done, is a rounding error. But it is a rounding error in a very specific place. Yesterday's earthquake occurred on the same plate boundary segment that produced, 13 years ago, an earthquake approaching magnitude 8, and it occurred on the western side of that segment, which is where the 2013 sequence started. Because the 2013 magnitude 7.8 did not arrive without warning. It arrived at the end of a sequence, and we will get to exactly what that sequence looked like because the shape of it is the entire reason anyone is paying attention this weekend. The reported moment tensor for yesterday's earthquake gives 2 possible fault planes, and both of them are close to vertical. The dips come in at approximately 87 degrees and 84 degrees with rake values close to pure horizontal motion. In plain language, this was almost perfectly clean strike slip. The crust slid sideways past itself. It was not shoved upward, and it was not dropped downward in any meaningful amount. That mechanism is the reason there was no tsunami, and it is worth being precise about why. Tsunamis are generated by vertical displacement of the seafloor. The ocean has to be physically lifted or dropped for a wave to be born. Sideways motion moves an enormous amount of rock and displaces almost no water. So the Pacific Tsunami Warning Center did not have to model anything complicated to clear this event in 7 minutes. The focal mechanism answered the question before the modeling started. The depth figure needs a caveat, though, and it is one that almost never survives into news coverage. When the survey reports a depth of exactly 10 kilometers, that number is very often not a measurement. 10 kilometers is a fixed default the agency uses when the available station geometry cannot constrain depth properly. It signals shallow far more reliably than it signals 10. And in this case, a reviewed moment tensor solution reported for the event gives a centroid depth of approximately 11.5 kilometers, just over 7 miles. Still firmly shallow, still consistent with rupture in the upper crust, but a real number rather than a placeholder. Shallow matters here. A shallow strike-slip rupture on a transform boundary is a fault behaving exactly the way that fault is supposed to behave. There is nothing exotic about it, which is, in a way, the problem, because the 2013 sequence was also a fault behaving exactly the way it was supposed to, right up until it wasn't. There is a genuine ambiguity in the record from yesterday, and it has to be handled honestly because it changes the interpretation completely. Some of the early reporting describes a magnitude 5.7 earthquake in the Scotia Sea, occurring roughly 7 hours and 42 minutes before the magnitude 6.2. That would place it near 0:40 Universal Time on the 22nd. But at least one news aggregator carried a preliminary magnitude 5.7 item that appears to describe the same event, the one that was later revised upward to 6.2 as more stations reported in. So there are two readings, and both are still live. Under the first reading, two separate earthquakes occurred. A magnitude 5.7 struck first, and a stronger magnitude 6.2 followed nearly 8 hours later in the same general area. Under that reading, the smaller event is a foreshock, and the sequence has real structure to it. Under the second reading, there was one earthquake. The 5.7 was an automatic preliminary solution for the 822 event, refined to 6.2 by human review, and the sequence is an artifact of how quickly automated systems publish. This will be settled within days by the reviewed catalog, and it will not be settled by anyone's intuition today, including mine. But it is worth understanding what is actually happening when a magnitude changes, because people read those revisions as evidence of something being hidden. The first number out the door is generated automatically from a handful of stations within minutes. The final number comes from a human analyst working with the full global dataset hours later. A magnitude that moves is not a magnitude being covered up. It is a magnitude being computed properly. There is a third earthquake on the map this week, and it is going to get lumped in with the other two by coverage that should know better. Farther east, in the South Sandwich Islands region, a magnitude 5.4 was recorded at a depth of approximately 159 kilometers. That is nearly 100 miles below the seafloor. And that depth is the entire point, because an earthquake 159 kilometers down cannot be mechanically related to a 10-kilometer down strike-slip rupture more than 1,000 kilometers away. It belongs to a completely different tectonic environment. The South Sandwich system is a subduction zone, where oceanic crust is descending into the mantle and generating intermediate depth earthquakes inside the sinking slab. The South Scotia Ridge is a transform boundary, where two plates grind past each other sideways in the upper crust. These are two different machines that happen to be attached to the same plate. Calling all three events a swarm is the single most common error this story is going to produce over the next few days, and it is worth getting right, because the whole argument that follows depends on knowing which earthquakes are actually connected to each other. The South Scotia Ridge is the southern boundary of the Scotia Plate, where it meets the Antarctic Plate. It is a predominantly left lateral strike-slip transform, sinistral in the technical language, carrying a component of extension in places, which the literature describes as sinistral transtensional. It is not a single clean fracture. Published work describes a structurally messy margin, old continental fragments, sunken basins, bends in the boundary trace, zones where the crust is being pulled apart, and zones where it is being squeezed. And the slip rate is slow. Peer-reviewed work puts it at approximately 7.4 to 9.5 millimeters per year, and the survey quoted roughly 11 millimeters per year in its 2013 event materials. For comparison, the San Andreas system moves at roughly 30 to 40 millimeters per year. The South Sandwich subduction zone, at the eastern end of this very same plate system, converges at 70 to 78 millimeters per year. The same plate runs at two speeds that differ by a factor of 10, depending on which edge you're standing on. That slowness cuts in two directions at once, and it is a mistake to resolve the tension too quickly. Slow boundaries take longer to reload, so large earthquakes on them are rarer. But slow boundaries also accumulate strain for a very long time between events, and the arithmetic is straightforward. At 7 to 11 millimeters a year, a fully locked segment banks about 1 meter of slip deficit every 90 to 135 years. When a boundary like that finally goes, it goes big. 2013 proved it. Here's the part that should genuinely unsettle you. According to the survey, there are no land-based observations anywhere within the Scotia Plate to measure plate motion. None. All reported motions for this plate are derived from remote earthquake recordings. There is no permanent satellite positioning network cemented to this plate telling us how it is moving in real time. There is no strain meter. There is no continuous geodetic record of any kind. Everything we know about how fast this plate is traveling, we know because it broke and we listened from thousands of kilometers away. This is a plate we can only observe when it fails. And that single fact is why the question raised by yesterday's earthquake is so difficult to answer. Not because the science is weak, but because the instrument that would answer it does not exist. To understand why anyone is watching this weekend, you have to look at what happened in November of 2013, day by day. On Wednesday, the 13th of November, a magnitude 6.1 struck the South Scotia Ridge approximately 50 kilometers west of a point that meant nothing to anybody at the time. It was reported the way yesterday's earthquake was reported: remote, moderate, no damage, no tsunami, no story. On Friday the 15th, a magnitude 6.8 struck very close to that first event. Now there was a sequence, and the British Antarctic Survey later reported that more than 40 earthquakes exceeding magnitude 4.4 struck the region from the 13th of November onward. On Sunday the 17th, at 9:04 and 55 seconds Universal Time, a magnitude 7.8 ruptured the boundary. It was the largest earthquake ever measured in the Scotia Sea region, more than 50 years of instrumental record at that point, and the third largest earthquake anywhere on Earth in 2013. The rupture propagated primarily eastward across roughly 311 kilometers of plate boundary, and published analysis describes it as a multi-part rupture with 5 separate sub-events running at average velocities of roughly 0.6, 2.6, 2.3, 2.8, and 3.0 kilometers per second. It did not tear at a steady speed. It stuttered, accelerated, and jumped. Within 8 hours of the main shock, 20 aftershocks between magnitude 4.6 and 5.3 occurred near the epicenter, and all of them aligned along the southern boundary of the Scotia Plate. The aftershock distribution mapped the fault trace itself, 4 days. That is the interval from the first moderate earthquake to the main shock. And the first event in that chain was a magnitude 6.1, about 50 kilometers west of where the big one broke. Yesterday's earthquake was a magnitude 6.2, about 67 kilometers west of where the big one broke. I want to state that parallel once, cleanly, and then attach the caveat immediately, because it is the strongest fact in this story, and it is also the easiest one to abuse. Foreshocks are only identifiable in retrospect. There is no observable property of a magnitude 6.2 that marks it as a precursor, rather than a standalone event, and the global base rate for any given moderate earthquake being followed by something larger nearby is on the order of a few percent. Most moderate earthquakes are just moderate earthquakes. That is the honest baseline, and it has to stay in view. The British Antarctic Survey, writing publicly about the 2013 sequence, put the mechanism at stake into one sentence. Quote, "The large events this week have all been strike-slip, horizontal displacement, movements related to Scotia Antarctic plate motion, which do not pose a significant tsunami risk. However, such sideways moving events can destabilize segments of a fault next to them in a sort of domino effect." End quote. That is not a claim from a comment section. That is a National Polar Research Institute stating in a public communication that events of exactly this type, on exactly this fault, can destabilize the neighboring segments. And the mechanism behind that language is well-established textbook seismology. It is called Coulomb stress transfer. When a fault segment slips, it does not simply release stress, it redistributes it. Some neighboring patches are relaxed, and some are pushed closer to failure, typically by fractions of a bar. It is a very small nudge delivered to a fault that may already be sitting a very small nudge away from breaking. Then there's the finding that reframes the entire question. In 2014, Yi, Lei, Kanamori, and colleagues published a study in Earth and Planetary Science Letters, volume 401, titled Complementary Slip Distributions, of the August 4th, 2003, magnitude 7.6, and November 17th, 2013, magnitude 7.8 South Scotia Ridge earthquakes. The title carries the finding. Complementary slip distributions means the two ruptures released strain on neighboring, largely non-overlapping patches of the same boundary. The 2003 earthquake, a magnitude 7.6 that struck on the 4th of August, that year at about 10 kilometers depth on the northern margin of the South Orkney microcontinent, broke one section. 11 years later, the next great earthquake broke the section beside it. Not the same ground again, the section next door. And that changes what question you should be asking. If large earthquakes on this boundary fill in unbroken patches rather than repeating on the same ground, then the question raised by yesterday is not whether 2013 is about to repeat itself. The question is which patch is still loaded and whether yesterday's magnitude 6.2 is sitting on it. Because the reassurance people reach for, 2013 already released the strain there, does not apply to the ground immediately west of 2013. That is the side that hasn't gone. There are people out there, and it is worth knowing who they are before we talk about what happens next. The South Orkney Islands are the nearest land to the epicenter. Coronation Island, Signy Island, Powell Island, Laurie Island, and a scatter of outlying rocks. 2 research stations operate in the group. Orcadas Base, Argentine, sits on Laurie Island. It was established by the Scottish National Antarctic Expedition in 1903 on the site of a stone meteorological hut called Omond House, and transferred to Argentina on the 22nd of February 1904. It is the oldest research station in Antarctica still operating, and it has been permanently populated continuously ever since. It stands 4 meters above sea level, roughly 170 meters from the coastline. The other station is Signy, run by the British Antarctic Survey at Factory Cove on Signy Island. It houses up to 8 people when fully staffed, and it closes for the Austral winter, which is right now. Signy is almost certainly empty as I record this, exactly as it was empty in November of 2013. Marine geophysicist Rob Larter of the British Antarctic Survey said at the time, quote, "I understand that no one has got there yet this season, but when people do get ashore, it is likely that they will find things have been shaken up a bit." End quote. One accuracy note, because a bad number is circulating. Some reporting places the western edge of the island group at roughly 50 kilometers from yesterday's epicenter. Calculated directly from the published coordinates, the distance to Signy Station is approximately 115 kilometers, and to Orcadas Base, approximately 160 kilometers. The outlying rocks are closer than the stations, but not 50 kilometers close. Call it under 100 miles and you are safe. There's a small piece of history in the name of the water, too. The Scotia Sea was named in 1932 after the Scotia, the expedition ship that carried William Bruce and the Scottish National Antarctic Expedition through these waters between 1902 and 1904. The same voyage that named this sea built the hut that became the longest continuously occupied base on the continent. The people who named this water left behind the one permanent human presence sitting beside this fault. 4 things are observable within days, and together they will confirm or kill the foreshock question. This is the practical part, and it is the part worth writing down. The first is whether the aftershock activity spreads along the boundary or stays clustered where it is. In 2013, 20 aftershocks mapped out along the fault trace within 8 hours. Migration along strike is the signature to watch for, and a tight stationary cluster is the opposite signature. The second is whether subsequent events exceed magnitude 5. This one has a hard number attached to it. Aftershock rates decay roughly as one overlapsed time. That is the Omori relation, and the largest aftershock in a sequence typically sits about 1.2 magnitude units below the main shock, which is Both's law. If yesterday's magnitude 6.2 was a main shock, the largest aftershock should land near magnitude 5.0. If events larger than magnitude 5.5 keep occurring over multiple days, then the 6.2 is not behaving like a main shock. That is a checkable threshold, and it is the single most useful thing a non-specialist can track this week. The third is whether the focal mechanisms stay consistent. If the following events show the same near-vertical strike-slip geometry, they are breaking the same structure. Mixed mechanisms would point to a more diffuse response spread across the messy geometry of this margin. The fourth is whether the activity migrates toward the 2003 or 2013 rupture patches. Movement of seismicity into the segments beside previous large ruptures is the specific case the domino language describes, and it is the one that would turn attention into concern. Let me be as clear as I can about what this is and what it is not. The base case, the overwhelmingly likely outcome, is that this was a moderate earthquake on a slow transform boundary that produces moderate earthquakes regularly, that its mechanism is consistent with known plate motion, that the aftershock sequence decays quietly, and that nobody remembers this in a month. That is where the odds sit, and I'm not going to pretend otherwise. But the reason this is worth 20 minutes of your time is that the alternative is not fantasy. The segment has demonstrated capability to magnitude 7.6 and magnitude 7.8 inside the last 23 years. The last sequence here opened with a moderate earthquake on the same side and escalated within 4 days. The dominant published model has large ruptures filling in the patches that have not gone, rather than repeating on the ones that have. And a National Research Institute has stated on the record that strike-slip events on this boundary can destabilize the segments beside them. None of that is a prediction. All of it is a reason to look. And the thing that makes this fault genuinely different from the San Andreas or the Nankai Trough or any of the boundaries we monitor obsessively is that we have no instrument standing on it. We cannot check the strain. We cannot see which patch is locked. Everything we know about this plate, We learn by listening to it break from thousands of kilometers away. So, when a magnitude 6.2 lands 67 kilometers west of the largest earthquake this region has ever produced, on the same side that the last sequence started from, we are looking at the only signal this boundary is capable of sending. We have no way to know yet whether it is the beginning of a sentence or the end of one. The reviewed catalog over the next few days will tell us which. Until then, the number to watch is magnitude 5.5.